Hello everyone. Today we will study the multiplication of vectors. So let's begin with the multiplication of vectors. The first thing in multiplication is multiplication of a vector by a scalar. So multiplying a vector by a scalar. Let's see what happens if we multiply a vector by a scalar. Say we have a vector A and I multiply it by certain number k. A कोई वेक्टर है, उसको हमने एक नंबर k से मल्टीप्लाई किया. Now अगर k पॉजिटिव है, if k is positive, then वेक्टर की डायरेक्शन वही होगी. Say this is our vector A and we have multiplied this by a number. So if k is positive, then the direction of the vector will remain unaltered. Direction change nahi hogi. And if k is negative, then the direction will be reversed. Say if this is k, this is a vector A and I multiply it by a negative number, then the direction will be reversed. It will be flipped by 180 degree. Next case, if k is a number more than 1, it's positive but more than 1, then the length of the vector will be elongated. अगर हमने k को वेक्टर को एक ऐसे नंबर से मल्टीप्लाई किया जो 1 से बड़ा है, तो वेक्टर की लेंथ सिंपली बढ़ जाएगी. So this is positive and more than 1, then the length will be elongated. So say this is ka in the same direction and a longer vector. And if k is a number less than 1, say it's a fraction, then the length will be contracted, length कम हो जाएगी, but direction will remain same. So if k is less than 1, length will be contracted, it will be lessened, but the direction will remain same. And if k is more than 1, then length will be elongated. And if k is positive, direction remains the same. And if k is negative, then direction is reversed. It's flipped by 180 degree. And one more point, if k is 0, if you multiply a vector by 0, then you get 0 vector. Say 0 into some vector A is 0 vector. You get null vector. We discussed about null vector, a vector whose magnitude is 1 and the direction is indeterminate. So this is what happens when a vector is multiplied by some number, by some scalar. Next, now we can have some example of this kind of multiplication. Say, you know this relation, a special case of second law of motion. Second law of motion, F is equal to ma. Here A is acceleration, mass is this is m is mass, which is a scalar, and this is vector. So vector is multiplied by a scalar. And similarly, momentum P is equal to m times v. V is velocity, which is vector, and m is mass, which is a scalar. So velocity is being multiplied by a scalar, by mass, and here acceleration is multiplied by mass, which is a scalar. So this was these were some examples of a vector being multiplied by a scalar number. Next, let us see multiplication of two vector quantities. What happens when we multiply two vector quantities? Now, in physics, we combine two different quantities to produce a new quantity. For example, you know speed, from your high school physics, you know speed is equal to distance upon time. Or if you have to write distance, then distance is equal to speed into time. So here we are multiplying speed and time to get distance, and here we are dividing distance by time to get speed. So different quantities are combined, and what I mean by combination is multiplication and division. Addition and subtraction is always performed for same type of quantities. Different quantities cannot be added or subtracted. So by combination I mean multiplication or division. So we combine different type of quantities to produce a new quantity. Similarly, if the quantities are vectors, if we combine vector quantities, say we have two vector quantities and the multiplication of vectors produces a scalar quantity, then we call this type of multiplication scalar product. And if the combination produces a vector quantity, then we call this vector product or vector multiplication. So we will have two types of multiplications. One is scalar multiplication and the other will be वेक्टर मल्टीप्लिकेशंस. अगर दो वेक्टर क्वांटिटीज को कंबाइन करके मल्टीप्लाई करके स्केलर क्वांटिटी मिल रही है, देन उसको हम कहते हैं स्केलर प्रोडक्ट. और अगर दो वेक्टर्स को मल्टीप्लाई करके हमें वेक्टर क्वांटिटी मिल रही है, देन वी कॉल इट वेक्टर प्रोडक्ट. एंड द स्टाइल ऑफ राइटिंग इज डिफरेंट फॉर बोथ द प्रोडक्ट्स. द स्केलर इज रिटन लाइक दिस. Say we have two vectors A and B and we are multiplying them, so it is written as A dot B here, and here we write A cross B. So to distinguish the style of writing, we put a dot here and we put a cross here, and because of this dot we also call this dot product. So either scalar product or dot product, and because of this cross we also call this cross product. So either vector product or cross product. And now let us see this one first. What is dot product or scalar multiplication? So let us first see scalar multiplication. Scalar or dot product. Say we have two vectors, vector A and vector B, and this is the angle between the two vectors, theta, and we are calculating the dot product. So A dot B. Now how it is calculated or how it is defined? We define that dot product is the component of one vector in the direction of other vector multiplied by the magnitude of the other vector. Or we have studied about the components, how we find the component of a vector in a certain direction. So again, the dot product is component of one vector in the direction of other vector into the magnitude of the other vector. For example, if I want to write the component in the direction of B, so you know जिस तरफ थीटा होता है उस तरफ component cos के टर्म में आता है. The component in the direction of B will be A cos theta. And similarly the component of B in the direction of A will be B cos theta. So the component of one vector times the magnitude of the other vector. Component of one vector in the direction of other vector times the magnitude of the other vector. So we can write it like this: component of A in the direction of B times the magnitude of B. Or we can write it like this: A, the magnitude of A times component of B in the direction of B, which is B cos theta. And here this will be a scalar, this will be just numbers, so I can write it like this without bothering about the orders. We can write it like this: AB cos theta. So A dot B is equal to AB cos theta. And remember, A is magnitude of vector A and B is magnitude of vector B, and cos theta, where theta is the angle between the two vectors. So this is how dot product is written. And why we write it like this, we will see when we will see the application. When we will be studying work energy, then we will see the application of the dot product and many other applications. And the dot product, the self dot product, say if I multiply A by the same vector A. If I write A dot A, the dot or scalar product of same vector, then A and A will be in same direction. So it will be just A times A and same direction, so angle is 0, so cos 0 is 1, so this becomes simply A square. So self dot product is simply the square of the magnitude. And you can easily see here that the scalar product is commutative. I can write it like this: A dot B can be written as B dot A. It doesn't matter what's the order, A dot B is equal to B dot A, so scalar product is commutative. Next, we can discuss some cases here. Let's see some special cases. See here. Say the angle between the vectors is 0 degree. So theta is 0 degree. Then A dot B will be equal to, from here, A, B and cos 0. So it is just A into B. Cos 0 is 1. So A dot B is equal to simply simply AB, which is also the maximum of the dot product. How much can be the maximum value of the dot product of two vectors is simply AB, and theta is 0. So theta 0 means the vectors are parallel, they are in same direction. So when the vectors are in same direction, the dot product of theirs is maximum. Next case, what if the angle between the two vectors is 180 degree? If the angle between the vectors is 180 degree, which means the vectors are anti-parallel, they are in opposite directions. And then from the formula, A dot B will be equal to A, B, and cos of 180 degree is minus 1. So it becomes minus A into B, which is also the minimum value of dot product of two vectors. So for which angle the dot product will be minimum, it is 180 degree, and the value is minus AB. Next case, what if the angle between the vectors is 90 degree, that is the vectors are perpendicular. So A dot B, third case, the angle is 90 degree, or the vectors are perpendicular. Then A dot B will be equal to AB, and cos 90 degree is 0, so it is simply 0. So A dot B is 0, and this is a very important case that says that if the two vectors are perpendicular, then their dot product will be 0. And it is true conversely also, that if the dot product of two vectors is 0, then certainly the vectors are perpendicular. So it is also the condition of two vectors being perpendicular. If the dot product of two vectors is 0, then the vectors are perpendicular. And if the vectors are perpendicular, then the dot product will be 0. So these are some cases associated with the scalar or dot product. Next thing. One more point I can discuss for obtaining some direct results. If this angle is acute, that means it is between 0 and 90 degree. The angle is acute. Then कि इस range में, in the range between 0 and 90, cos theta is positive. So in this range, cos theta is positive. Then the dot product will surely be positive. So if the angle between the two vectors is acute, between 0 and 90 degree, the dot product will be positive. Next, if the angle is obtuse, that is more than 90 and less than 180 degree, the angle is between 90 and 180, then cos in this range is negative. Cos theta in this range is negative. So dot product A dot B will be negative. So for obtaining some direct results, we look at the theta at the angle. If the angle is acute, then dot product will be positive, and if the angle is obtuse between 90 and 180 degree, the dot product will be negative. Next we can discuss some applications of dot product here. The dot product, this expression can be used to arrive at certain results. Let us see. So we have written A dot B is equal to AB cos theta. A dot B is AB cos theta. Now, if you want to calculate this cos theta, then you can simply see cos theta will be equal to A dot B upon this A into B. Remember, A and B here, they are vectors, and in the denominator, they are just magnitudes. So here A and B are magnitudes, and here A and B are vectors. So if we can find this ratio, that will be equal to cos theta, or theta will be equal to cos inverse A dot B upon the product of the magnitudes AB. So this result, this is how we can calculate the angle between the two vectors. And remember, if this dot product is 0, then cos inverse 0 gives you the theta is equal to 90 degree. Next application. So we have seen that if the two vectors are like this, say angle between them is acute, this angle. And here is the expression for dot product. A dot B is equal to AB cos theta. Now, what if I write just B cos theta? Just B cos theta. So B cos theta will be equal to A dot B, and this will go in the denominator. So B cos theta is equal to A dot B upon A. And now what is B cos theta? See here, B and A, an angle between them is theta. So the component of B in the direction of A is B cos theta. So this is the component of B along A. Similarly, we can write, if you want to write A cos theta, then B will go in the denominator. So what is A cos theta? This is A dot B upon B. So what is this? See here. This is vector A and this is theta. So component of vector A in the direction of B will be A cos theta. So A cos theta is the component of A in the direction of B. So if we can calculate dot product, we can also calculate component of one vector in the direction of other vector. And how we will identify that which component is in what direction? The letter appearing in denominator will tell you the component in which direction. Here it is A, so this is the component of A this is component of B in the direction of A. This gives you the direction in which the component is calculated. So this is component of B in the direction of A. This is component of A in the direction of B. This component is calculated in the direction of B. So the vector appearing in denominator will tell you the direction in which the component is calculated. So I can write that this is component of vector A along, this is not component of A but component of B. So this is component of B along A, and this is component of A along B. Now you can see that A dot B will be scalar, it will be just a number, and here it is magnitude. So this whole thing is a scalar. And if I want to make it a vector, then what to do? So last time we have seen that unit vectors are used to indicate the direction. So if I want to make this number A dot B upon A vector, so this is, remember what is this? This is component of vector B in the direction of A. So you have to put the direction of A here, that is unit vector A. So this makes the whole thing a vector quantity. this is the magnitude, and this is the direction. So this is the component of B in the direction of A, and this is unit vector in the direction of A. Similarly, A dot B upon B, this is component of A in the direction of B, so we put the direction of B, a unit vector in the direction of B. So if you want to calculate just the value of one of the component of one vector in the direction of other, just find A dot B upon A or A dot B upon B. And if you want to know the whole vector part of one vector in the direction of other, then we have to put a unit vector also there, and this unit vector will be in the direction in which we are calculating the component. So these are some applications of dot product. Next, we have studied about unit vectors along the coordinate axes, x-axis, y-axis, and z-axis, and those were I cap, j cap, and k cap. So let's see how the dot product is carried in case of unit vectors. So in case of unit vectors, in 3 dimensions along the 3 coordinate axes, so what will be I dot I? I cap is a unit vector along x-axis. Now what will be I dot I here? So A dot B, remember A dot B is equal to A B cos theta. Here A magnitude, B magnitude. So we'll have to write the magnitude of I and magnitude of I, and angle between I and I is 0, so it is cos 0. Then you know the magnitude of a unit vector is 1, so this is 1 into 1. Cos 0 is also 1, so the final result is 1. So I dot I is equal to 1. And we have discussed a point that self dot product will be square of the vector. So you can also write it like this. That this is square of I cap. Magnitude of I cap is 1, so 1 square is again 1. So I dot I is 1. Similarly, j dot j and also k dot k will be equal to 1. So I dot I or j dot j or k dot k, they all will be equal to 1. Next, what if the dot product, if we take the dot product of I with j? What is I dot j? Here I is along x-axis and this is along y-axis. So certainly angle between I and j is 90 degree. So dot product is 0. The dot product of 2 perpendicular vectors is 0. Similarly, if we take the dot product of j with k, k is a unit vector along z-axis. This goes to 0 also. And k dot I, z-axis, x-axis, this is also 0. So self dot product will be 1, and if we take the dot product of unit vector I with any other unit vector j or k, the dot product will be 0. Next, let's multiply 2 vectors in component form. If the vectors are given in component form, we have discussed that a vector can be written in its components. So what if vector A is equal to some ax I cap and ay j cap and az k cap, and another vector B, bx I cap and by j cap and bz k cap. We have discussed about these types of vectors in last lecture. So what will be A dot B? So to find the dot product, or simply to multiply this by this, we can use the trivial method that we take one element and multiply it by all the 3 in the next vector, then again take this element and multiply it by all the 3 elements, and so on. Now, what will happen if we multiply this by this? So ax times bx, ax times bx, and what is I dot I? We have seen about it. This is just 1. And next, when we multiply this by this, we get I dot j, which is 0. So no need to write here. Then I dot k, that is also 0. So all the two parts are 0. Next, take this element, so multiplied by bx. Here j and dot I will be 0, and j dot j is 1. So this is just a y and by, and then j dot k will again be 0. So we don't write it. Next, we take this element multiplied by this one. So k dot I 0, k dot j 0, and k dot k is 1. So we get just az and bz. So if the vectors are given in the component forms, then what to do? Just take the x components and multiply them, and then y components, multiply them together, and then z components and multiply them together. And remember, you may think that this is the x component of the scalar product and this is y component of the scalar product, or this is z component of the scalar product, which is not the case. These are just numbers, and for final result you will add all these numbers. Scalars don't have components. For example, let's take an example in numeric. Say we have a vector A is equal to 3i plus 4j plus 5k, and other vector, say I minus 2j and plus some k just. And we have to find A dot B. So we take x component 3, and here 1, just multiply it. 3 into 1 is 3, and no need to multiply it by other components. Then take y component, and here y component 4 into minus 2 is equal to minus 8, and 5 here and 1 here, so that is plus 5. Now 3 minus 8 plus 5. How much is this? I think this is going to be 0. Yes, we got 0. This was A dot B. So A dot B here is 0. Now we can conclude that A and B are vectors. If these two vectors are perpendicular, the angle between these is 90 degrees because the dot product is becoming 0. So this was scalar multiplication of two vectors. Next, let us see the vector multiplication of two vectors. So vector product or cross product. Vector or cross product of two vectors. Say we have two vectors in this horizontal plane. You have to imagine this is a horizontal plane, and we have two vectors, say vector A and other vector B, and say there is some angle theta between the two. Now, how vector or cross product is defined? It is defined as the component of one vector perpendicular to the other vector. In scalar, we have taken the component of one vector in the direction of other, and here we will take the component of one vector perpendicular to the other vector into the magnitude of the other vector or the second vector. So A cross B, it's always written as cross. You should not read it as A multiplied by B or A into B. It's always written or said A dot B. Okay, so A dot B is equal to the component of one vector perpendicular to the other. Now, what will be the component of A perpendicular to B? So जिस तरफ थीटा होता है उस तरफ कंपोनेंट कॉस के टर्म में, एंड उसके परपेंडिकुलर डायरेक्शन में कंपोनेंट साइन के टर्म में. सो द कंपोनेंट ऑफ ए परपेंडिकुलर टू बी विल बी ए साइन थीटा times the magnitude of B, and cross product will give you a vector quantity. So we have to put a direction also. Now for direction we write a unit vector, and we can also write it like this. The component of B perpendicular to A, that will be B sine theta times vector A, and again a unit vector n cap. We have to put a direction there because the result is vector here. The combination produces a vector quantity. Okay, so we can write it A, B sine theta with a unit vector n. We will see what is the direction of this n cap. Can I write A cross B equal to B cross A? We will have to see if A cross B and B cross A both give you the same direction, then the cross product will be commutative. We will see about it. So A cross B will be AB sine theta, and if I want to know just the magnitude of the cross product, the magnitude of A cross B, then remove this direction and you get just AB sine theta. So the magnitude of A cross B is simply AB sine theta. And we can discuss two cases here. If the angle between the vectors is 0 degree, that means the vectors are in same direction, then you know sine 0, we will put 0 here. So sine 0 is 0. That means the cross product will be 0. If I write this in vector form, then this will be 0 vector, the vector of 0 magnitude and with indeterminate direction. And okay, I will draw this diagram again. What if the angle is 180 degree? That means the vectors are anti-parallel. Then A cross B, and I put sine theta, theta at the place of theta 180, sine 180 is again 0, so it is also 0. So if the vectors are parallel or anti-parallel, then the cross product will be a null vector or a 0 vector. So I can also say that if the vectors are collinear, they are on the same line, then their cross product will be 0. Or we can say it otherwise, conversely, that if the cross product is 0, then the vectors are collinear, they are on the same line. So this was about magnitude of the vectors of the cross product. Now what about this n cap? What is this n cap doing here? In which direction this n cap is? Let's find out. So I can write A cross B as AB sine theta with a unit vector n. To find the direction of n cap there, we use right hand rule. Right hand rule. As you can see, it is written right hand. That means you have to use your right hand, not your left hand. If you use your left hand, you will get the reverse, the opposite result. So always use your right hand rule. Now what is this rule? Now I say that the vector product is not commutative. That is, you cannot write A cross B as B cross A. They are not same. So this is not commutative. The cross product is not commutative, unlike dot product. Okay, so if it is not commutative, then the places are fixed. A is at the first place and B is at the second place. And here B is at the first place and A is at the second place. So keep the fingers of your right hand in the direction of first vector. Keep the fingers of your right hand in the direction of first vector, and the palm of your right hand in the direction of second vector. Then A cross B, or the direction of this n cap, A cross B or n cap, they are same. A cross B और n, दोनों की डायरेक्शन सेम है. This direction will be along your stretched thumb. So stretched thumb. The stretched thumb of your right hand will give you the direction of this n cap or simply A cross B. So to find the direction of A cross B, keep the fingers of your right hand in the direction of first vector and your palm towards the second vector. Then the stretched thumb will give you the direction of A cross B. Let's take an example. Let's say that, okay, I make the diagram in the plane of the board. These two vectors are in the plane of the board. Now, A is in rightward. So keep your fingers of the right hand in the direction of A. The fingers in the direction of A, that means towards right. And your palm towards the second vector, that is B. You can keep your palm like this, or like this, or like this, but you have to keep your palm like this. It should be towards the second vector. So keep your palm towards the second vector. Then stretched thumb in this condition is pointing out of the board. So for out of the board, we use a dot in the circle. This is outward direction. So A cross B here is out of the board. Now you can do it by other way also. Keep the fingers of your right hand in the direction of A and curl your fingers towards B or through the smaller angle. The smaller angle between A and B. So curl your finger through the smaller angle, then the thumb will give you the direction of A cross B. So either you can keep your palm towards the second vector or you can curl your fingers through the smaller angle. The thumb in those conditions will give you the direction of A cross B. And what about B cross A? So keep your fingers. If we have to find B cross A, let us see in which direction B cross A. So keep your fingers in the direction of B, and I can curl my fingers through the smaller angle, and then the thumb is going into the board. For into the board, we use a cross in the circle. So B cross A is into the board. B cross A is into the board, and A cross B is out of the board. Certainly they are just opposite. One is out of the board, the other is into the board. So I can say that A cross B is minus negative of B cross A. They are in opposite direction. So I can say that A cross B is minus B cross A. Let's take some more examples. Say we have vector A like this and vector B like this. Right hand rule, keep your fingers along the first vector. If you are calculating A cross B, then A is first vector. So fingers along the first vector and curl your fingers through the smaller angle, then thumb is going out of the board. So A cross B here is out of the board. And what about B cross A? So I keep the fingers, I have kept my fingers along B and curl your fingers through the smaller angle, and then thumb is going into the board. So B cross A is into the board. I can take one more example. Let's see. Now this is A. That means into the board. A is into the board, cross. And this is our B vector. B is towards right and A is into the board. So keep your fingers along the first vector. If you are calculating A cross B, then A is first vector. So keep your fingers along the first vector, that is into the board. And now in this situation, we cannot see where to curl the fingers. So just keep your keep your palm towards the second vector, that is B. So palm towards the second vector and fingers into the board, then thumb is going downwards. So here A cross B is downwards. And what is B cross A? So fingers along B, and this A is into the board. So palm, keep your palm into the board towards inward direction, then thumb is going upward. So this is B cross A. So you can clearly see here that A cross B and B cross A are just opposite. They are anti-parallel. So this way you can find the direction of A cross B or that n cap there. And we see that the cross product is not commutative. A cross B and B cross A are in opposite direction. And one more point that is very important. In all the cases, you see that A cross B or B cross A cross B or B cross A, say here A cross B is out of the board. So this is out of the board. Let me use this. This is out of the board. Now how much is the angle between this A cross B and the vector A? That is 90 degree. And also between A cross B and the other vector B, that is also 90 degree. The B is in the plane and this is out of the plane. So between A cross B and B, the angle is 90 degree. And this is true for every cross product. Say here, A cross B is out of the board. So this out of the board direction is perpendicular to both A and B. Here also, A cross B is perpendicular. You can see here, A cross B is perpendicular to B, and A cross B an inward direction. Inward and this direction, they are perpendicular. So in general, this is true that the cross product A cross B will always be perpendicular to both A and B. So A cross B, let's note it down, A cross B will be orthogonal to both A and B. A cross B will be orthogonal, that is perpendicular to both A and B, and this is true for all types of cross products. So this was cross product. Finding the direction is very crucial part of the cross product. Next, let us see how the cross product is carried if the vectors are in given component form. So let's apply cross product when the vectors are given in component form. Let us first see what will be I cross I. Clearly, both are in the same direction. Angle between them is 0. So this is 0. Similarly, J cross J and K cross K, they are all 0. So self cross product will always be 0. I cross A, J cross J, and K cross K, they are all 0. And what about I cross J or K, the cross product with other unit vectors? So say this is x-axis, this is y-axis, and this is our z-axis out of the board. And last time we have seen that we can we can take unit vectors. So say this is unit vector I cap, and this is unit vector j cap along y-axis, and this is our unit vector k cap along z-axis. Then what will be I cross j? So this is your first vector, this is your second vector, so keep the fingers along first and palm along second. Now fingers along first vector, which is I, and the other vector is upward, so keep your palm upward. Then in this condition, thumb is coming out of the board. So I cross j, I can write it like this: the magnitude of I times the magnitude of j and sine of the angle between I and j. That angle is 90 degree. And sine 90 is 1. And with a unit vector and cap. Now this is 1, and this is also 1. So 1 and a unit vector and cap. Then this is just a unit vector and cap. So find a unit vector in the direction of I cross j. What is I cross j? This is I, this is j, and thumb is out of the board, and out of the board direction is z-axis. So a unit vector along z-axis, which is what? K. So this is equal to K. So I cross j is a unit vector, that is K. What about j cross K? J cross K. J, y-axis. So keep your fingers along the y-axis, and K, z-axis outward. So fingers, J, and palm K out of the board, then thumb is along the z-axis. That means J cross K is a unit vector along x-axis, which is what? I cap. So J cross K is I cap. And then last, what about K cross I. K cross I. Now keep your fingers along z-axis, which is outward, and then your palm towards the x-axis, right side. So fingers along z-axis, outward, and palm towards right side, x-axis, then thumb is along y-axis. So J cross I will be a unit vector along y-axis, which is J cap. So I cross J is K cap, J cross K is I cap, and K cross I is J cap. We can calculate, we can find every time the direction, but it will be better if we can identify the pattern. Let us see what is the pattern. Here we have I, and this is J, and this is K. So every time when you multiply I with K, the cross product, so I cross J will be K, and J cross K will be I, and K cross I will be J. So if you go in anti-clockwise sense, then you will get I cross J plus K, and J cross K plus I, and K cross I plus J. So if you are moving in this circle along the anti-clockwise sense, then you will get positive unit vectors. And if you move in this circle in clockwise sense, that is I cross K, that will be minus J. Let us see here. I cross K. So I cross K. This is first vector. So keep your fingers along I, and K is outward, so palm outward. I cross K is a unit vector downwards. That means along y-axis, downward direction make unit vector. That will be what? Minus J. So you will get minus J. Similarly, when you move in the clockwise sense, I cross K minus J, K cross J minus I, and J cross I will be minus K. So from here it will be easy to remember the cross products of the unit vectors. Next, if the vectors are given in component form, then how we will calculate the product, the cross product? Let's take an example. Say we have two vectors, A as AXI cap, AY J cap, and AZ K cap. Another vector B as BX I cap, BY J cap, and BZ K cap. And we have to take the cross product of these two. So we will write A cross B. Again, you can go by the trivial method, that take one element and multiply it by the three elements, and then next element and multiply it by the three elements, and so on. But we have a better method. We calculate this by matrix method. I hope you have studied about matrices and determinants in your mathematics course. Let's see what is this matrix. We draw two perpendicular lines, and in the first arrow we write I, J, and K, unit vectors. And in second row we write the elements of the first vector. In first row I, J, K, and in second row we write the elements of the first vector, this A. So AX, X element, Y, AY, and AZ. Then in the third row we will write the elements of the second vector, that is BX, BY, and BZ. So this is how we will prepare the matrix. Now how to solve it? Let's see how we can expand it. First we take this element and the column of I and row of I. Leave it and you are left with these four elements. I के सामने का ये column छोड़ दिया and उसके सामने की row उसको भी छोड़ दिया. Then we have just these four elements. and multiply this element by this one, and then you will come come leftward. So AY BZ, and then come back, put a minus sign there. Let's write along. So we are expanding along I. So this column and this row will be left, and AY multiplied by BZ, AY multiplied by BZ, and come back and put a minus sign here, and then multiply this by this element. So BY into AZ, BY into AZ. So this is expansion of the matrix along I. Leave this column and this row, and then you have these four elements. So this into this minus this into this. So you get this row. Then we will expand along J and then along K. And in mathematics, you will study about it, that the expansion is alternate. Along I it is positive, along J it is negative, and then again along K it will be positive. So along J the expansion is negative. So we write minus J, and then leave this column and this row, the row of J and the column of J, and multiply this element by this element, AX and BZ, AX and BZ, and come back, put a minus sign, and BX and AZ, BX and AZ. So we have completed expansion along J. Now along K, and remember, plus, minus, plus. Expansion along I is positive, and along J negative, and again along K it is positive. So plus K cap. And leave this K column and K row, these four elements. So multiply AX with BY, AX, BY, come back, put a minus sign, and BX, AY, BX, AY. So this is how this matrix will be solved, or how these two vectors are multiplied through cross product. If you go by the trivial method, you multiply this by this, that will become 0, because I and I cross product will be 0. But if you multiply this by this, you will get I cross J, and then here you will get I cross K. It becomes sometimes tedious to remember what is I cross J and what is I cross K. So I find this method easier to find the cross product of two vectors if they are given in component form. We will see the examples of this cross product when we will be studying rotational dynamics. Next, let's take a question. So we have this question. Two vectors are given to us, A, X, and AY, J, and AZ, K. So this is a vector in component form, and another vector, BX, I, and BY, J, and BZ, K. We have to find a unit vector which is perpendicular to both these two vectors. So the vector should be unit vector and perpendicular to both A and B. Now how to find a vector which is perpendicular to both A and B? So we have discussed that A cross B will be perpendicular to both A and B. So the cross product of these two will be a vector which is perpendicular to both A and B. And then how to find the unit vector? We discussed last time that if X is a vector, then it can be written as the magnitude of X times the unit vector. So unit vector will be equal to vector upon its magnitude. So if this is a vector and we want to find a unit vector in this direction, so just divide this by its magnitude. So this is a vector which is perpendicular to both A and B, and its magnitude will be 1. So this is a unit vector perpendicular to both A and B. Unit vector perpendicular to both A and B. So this was cross product, the multiplication of vectors by the method of cross or vector product. And before that we have seen the multiplication of two vectors by the method of a scalar or dot product. So this was it, all about the vector, the algebra of vectors. And as we go along the course, then time to time we will be applying the concepts that we have developed here in kinematics and then in laws of motion and work energy and then rotational dynamics. We will be using these developments, these concepts or methods. So these are very handy. These they serve as tools to study physics. Without the vector algebra, it will be very difficult to understand the vector quantities. It will be very difficult to comprehend the behavior of vector quantities when we will be dealing with motion and some complicated kind of motions. Now, so after this much discussion, let's try to define a vector again. What is a vector quantity? There are certain quantities which show some behavior of vector quantities, but they are actually not vector quantities. Let us see. So let's write down the definition of a vector. How can we define a vector? Initially we have discussed that a vector is a quantity that has magnitude and direction. जिस भी क्वांटिटी को डिस्क्राइब करने के लिए completely magnitude and direction दोनों की जरूरत हो, we call that a vector quantity. But there is some more things to this definition. Okay, so a vector must have magnitude and direction. And next thing we have studied about the addition of vector. So if a quantity is vector, it must follow the addition law of addition of vectors. Sometimes we associate a direction with certain quantities, but they do not follow the vector law of addition. So next property of a vector will be that it should follow the vector law of addition. Vector law of addition. And the third property that it should have, that is, the addition should be commutative. The addition should be commutative. If the addition of two quantities is not commutative, then they cannot be vectors. Commutative means if you add A and B, or if you add B and A, you get the same result. That is being commutative. Now let's discuss some quantities which deviate from these properties. They show some behavior of vector quantities, but they are actually not vectors. We have a quantity time. We can associate a direction with time, that it is from past to present to future. That's the direction of time. The time flows in this direction from past to present to future. Now this is a very specific direction. This is a very unique direction. You don't need to state it. You can always understand that this is the direction of the flow of time. We cannot state it. इसको हमें बताने की ज़रूरत नहीं पड़ेगी. Time has this direction. So this type of quantities cannot be vectors. If the direction is not required to be stated, then the quantity is not vector. Similarly, pressure. Pressure is always perpendicular to the surface. So we will always know in which direction is the pressure. The pressure is acting in what direction, we will always know. So we don't need to specify the direction. We don't need to state the direction. So vectors, so pressure cannot be a vector quantity. A vector quantity must have a direction that needs to be stated. If it has a unique direction that needs no statement, then it cannot be a vector. Similarly, there is a quantity current. In circuits, we always show the direction of current. Say in this segment of wire there is a current 3 ampere. Ampere is the unit of current. And in this segment of wire there is a current 4 ampere. Then if 3 ampere current is coming from this direction and 4 ampere current is coming from this direction, then in this segment of wire there will be 7 ampere current. Now this 7 is independent of the angle between the two wires, between the two currents. Whatever may be this angle, this current is always 7 ampere. So the resultant is independent of this angle. Though we are associating direction with currents, we are putting an arrow over these segments, but the addition of currents doesn't follow the vector law of addition. We cannot add here. We can add the currents just like numbers. 3 plus 4 is always 7. We have directions, but they do not follow the vector law of addition. So current is not a vector quantity. Next, let us take a quantity that is angular displacement. We can associate a direction, we can give a direction to the angular displacement, but the addition of angular displacement is not commutative. Let us see an example. Say we have this book in my hand, and the cover page, the front cover page is upward, and I will rotate this book in about 2 axes, and if the final orientation of book is same, I will rotate this book by 2 ways. Say if I rotate this book through an angle theta and then through an angle phi. So theta plus phi should be equal to phi plus theta. If it can show this kind of behavior, then the angular displacement will be vector. Let's see if it follows this kind of commutative behavior. So the front of the book is upward, and I'm going to rotate it. So let's first decide, this is our z-axis and this is our y-axis, and once more, this is our x-axis, this is our y-axis, and this is our z-axis. So I will rotate this book first along about x-axis, and then about y-axis. So one angular displacement about x-axis by 90 degree, and then another angular displacement about y-axis again by 90 degree. So I will first rotate it by x-axis and then y-axis, and next I will first rotate it by y-axis and then about x-axis. So let's first rotate it about x-axis, okay, and now about y-axis. So this is the orientation of the book. Keep this in mind. I can reverse it. So one more time, rotation along x-axis and rotation along y-axis. This is the orientation of the book. The front of the cover is towards right of me. Okay, now next, let's first rotate it along y-axis and then about z-axis. So I first rotate it about y-axis and then rotate it about x-axis. Now this is the orientation. If you can remember, this wasn't the case previously. Previously this cover page was right to me. Now this cover page is towards you. So the final orientation of book is not same in these 2 cases. So if you rotate it by about y and then about x, and the other way, first about x and then about y, you will not get the same result. That means the addition of angular displacements is not commutative. You may associate a direction with the angular displacement, but the addition is not commutative. So angular displacement having direction but not following the commutative property is not a vector quantity. But if your angular displacement is very small, then let's see what happens. So this is book, and first rotate it about this x-axis, a very small angle about x-axis, and then about let's first rotate it about x-axis, and through a very small angle about this axis, about z-axis. So through a small angle about x-axis, and then about z-axis. So this is the orientation of the book. Now let's do it the other way. First about z-axis, and then about x-axis. So this is the orientation of the book. So this is somewhat like the previous one. The book is in the same orientation if you rotate it by the two methods. So I can say that small angular displacements, they are somewhat commutative. So they are vector, but large angular displacements, they are not vectors. Large angular displacements are not commutative, while small angular displacements are commutative. So a vector quantity must have a magnitude and direction that can be stated, that needs to be stated. It must not be unique. And then it should follow the vector law of addition. We have seen that electric current doesn't follow the vector law of addition. And next, the addition of vectors should be commutative. We have seen that angular displacement, large angular displacement, is not commutative. So this is how the vector is defined in more sophisticated way. So this was it, the basic of vector analysis. Hope it was helpful for you. And next you can find a different segment on this channel for questions on vectors. We will try to solve some basic questions from the NCERT textbook, and as well as the NCERT exemplar problems, a supplementary book. And email me and engage with the School of Physics on different platforms. See you again. Thank you.